maybe this meeting will end after 40 minutes and then maybe you have to restart it. Oh no, the live stream is fine. But okay. Oh, everybody is online today. It's weird. Okay. Everybody can hear me, right? Am I audible?
Yes, sir.
Yeah, in case I'm not, then just tell me. Okay, so first of all, any questions from last class? Anything you want me to repeat? Except the whole thing, yeah, I want to repeat the whole thing, but if there's something particular you can point out which you want to repeat, or which you want to see in detail. So there are some details which I skipped because I think those you can just read in a book. They're not very interesting. But if you want to see some detail, you can also say that, and I can see if I want to present that. Or maybe you haven't read the book yet. That's the other possibility. Okay, no worries. Yeah, hopefully you will read the book, and yeah, please read it soon, because otherwise you will forget the class experience, and then you won't be able to match it. Although the video is recorded and it's available on YouTube, but still, you know, it's good to just do it early. Okay. Okay. So then today I will just move on. So today I want to talk a bit more about PC dimension, and in particular, I want to finish the story from last time. So last time we said that, hey, if you know the growth function of some hypothesis class, then you can get some bound on the learnability. So particularly, we got some bound of this type. So if a growth function is tau h for some hypothesis class h, then we said that yeah. So the probability 1 minus delta, the difference between the true loss, of h, and the empirical loss of h is going to be small. It's going to be at most something like 1 over delta times something like square root log tau h of 2m by square root with some factors, so approximately. So there are some factors that I have not written, but roughly it was this. Yeah, where S is m samples. S is samples on. And so we showed something like this. Yeah, and maybe just to be a bit more concrete, in class we actually showed something a bit stronger. So we actually showed that the expectation of this. Okay. So this thing is true for all hypotheses. But in class we did not do this thing exactly. In class we tried to show something slightly stronger. We showed instead that the supremum of this. Yeah, the expectation of the supremum. So sample your S, and you take the average over the samples. Where of what quantity? For every S, you ask for the maximum possible difference over hypotheses of these things. Okay. So we show that this quantity is at most. So yeah. So this is what we showed in the class. And then the statement which I wrote earlier, the high probability bound and the probability by minus delta. Okay, so all this is without any probability. There's no probability. So this is this is the statement about expectations. There's no randomness in this statement. But then you can turn it into a high probability bound by using Markov inequality. Right. So in general, okay. So in case someone doesn't know, or yeah. So in general, for random variable, if expectation of x. Okay. So this is simple bound that probability that x is more than some t. Is most expectation of x by t. Okay. So assuming everything is positive. Yes, so assuming x is non-negative variables, this is always true. So so saying that if expectation is small, then it's unlikely that the variable will be too large because this bound is at most expectation by t. And then we did just that actually. So this here is a bound on the expectation of this. And then the chance that this quantity here, this is your x, the chance that this quantity here is too big. The chance that this quantity is bigger than this divided by delta is going to be only 1 minus delta. It's going to be delta. So if I use this inequality, it gets me that probability that this thing is more than this thing by delta. Okay, so so just use that, right? So probability that x is more than so this thing here is t. This is at most the expectation, which was this thing, divided by p, which is this whole thing. So this probability, so probability that this event happens is small. So this event happens is less than delta. So this probability is smaller than delta, and so the probability by minus delta, this thing here is actually smaller than. So so that's the whole picture. Which I did not write last time, but this you can figure out yourself. And there's also given the book, you can just look it up. Okay, so just a small thing. So sure, no questions about any of this. But any part of the proof, the SS prime argument. Okay, maybe let's sketch the proof anyway, just to in case anyone does have questions. So what we did last time is that so first we turned our problem of bounding the expectation on this. Now I erase this. So so we have to bound the expectation of this, and I'm going to show that it's at most this thing. So so first step was to somehow turn this expectation into expectation over two samples. So right now you have an entire distribution and a sample, which is difficult to work with because this is an entire distribution. It's hard to think about it. So we turned it into something about two samples, S prime and S. So now you have two samples and S prime. So that was the first step. Then second step was to say that okay, I can take an average over these two samples, two m samples now. So S and S prime are both from D drawn m times. So so then basically I have this entire space here of SS prime possibilities. So each point here is some SS prime. So this is some S1 prime. This is some S2 prime. And so you have this huge space of SS prime possibilities. For each possibility here, I'm looking at the maximum over every hypothesis in my class of the difference between the two empirical losses between S1 and S1 prime. And yeah, taking the max. And now I want to average these maxes out, average these supremums out over the different S1 prime, S2 prime possibilities. And here, these are terms of distribution. So you weight every point by its corresponding probability mass in the distribution. So yeah, and that's how you get the weighted average, and that's just expectation. Yeah, and now we said that okay, this is quite difficult to work with because our hypotheses are because we are not hypotheses. Right? The only tool which we really have is that if you had this one hypothesis, then hopefully if you have a lot of if you're averaging over a lot of samples, so you have this one hypothesis and you average over many pairs, over many SS prime pairs, then using some concentration, you will get a small error. Yeah, but this is for one guy. Now in our hypothesis class, we have a lot of guys, we possibly even infinite. So cannot just multiply the small error by infinite. Yeah, that will not lead me anywhere. So what I did instead is that we said that okay, we use the fact that our growth function here is small. This is some quantity we have in our control. So we said that okay, I will not average out over the entire space because that will cause me to multiply my whatever little part I have for this difference for one hypothesis with some huge number of hypotheses. So instead, I will divide up this. I will carve up this big space into small parts, so that for each part, the number of distinct hypotheses is small. So we break it up into small parts. Right, and so remember we had a table. So every row of a table was some point here, and so every part which I'm drawing here is some shuffling of a row of the table. So so what's a part here? A part here is just an equivalence class. So so we say that some S1 prime and S2 prime might be the same class and the same part here if I can obtain them using some simple manipulation. So if I can obtain S2 prime from S1 prime by shuffling the by switching around the ith sample in S1 with the ith sample in S1 prime. So I think we have an example there, something like let's say S1 is 8372, S1 prime is 10 minus 1 5 6. So this is S1 prime, and then maybe I can get S2 prime by switching around the ith samples in S1 prime. So if I switch these two, I get 10 8. Maybe I don't switch these two, I get 3 minus 1. Maybe I switch the next one, I get a 5 7. Maybe I don't switch the next one, I get 4 6. Okay, so if this is S1 prime, S2 prime, then they're in the same part here. So you have S1 prime here and S2 prime here. So they're in the same part here. And then I will average out over each part. So there are some 2 to the n, perhaps maybe a bit less, but if there are repetitions. But roughly speaking, you have 2 to the n points in each part, because for every index you can choose to switch or not switch. and then I will do my averaging. So for a given hypothesis H, I will only average over each part. And then I will again say using concentration that since I have 2 to the n, I have a lot of these different things. Using Huffing bound, some concentration inequality, I will get that this average here. So for fixed H, the average of this thing, the two empirical mean losses is small over this part, and then since inside each part the sample the sample points themselves, the sample multi-sets themselves are the same, right? So it is the same samples just shuffled around. The distinct hypotheses for this sample sequence and this sample sequence are the same because they are the same. It's the same multi-set just shuffled around. So you have some tau h of 2m, in this case 8, different distinct hypotheses, which are relevant for each of these different 2 to the m sample sequence pairs that you can generate, and so you can just multiply the small average that you got for your 1h with tau h of 8. Yeah, so you really cannot be. So the maximum they cannot be more than that. Yeah, so that was really the whole that was that. And then then remember this average we got using some Huffing bound. We average out over these shuttles, these swaps, and if you manipulate that Huffing bound calculation, then you will end up with this quantity. So so that is a double manipulation. There is no deep concept in that. So that was the whole picture in case someone was. And then on top of it, you apply this Markov inequality, and you get the high probability count for parallel inequality which you wanted. So you put so to t you put t equal to this over delta, and then you get what you want. Okay, so in case someone has questions, you can ask. It's a good moment to ask because I think now everything is on the board. All the tricks. Okay, maybe ask a simple question. So where in this whole argument did we use union bound? Somewhere we use union bound. So where did we use it? It's somewhere we use the union bound probability that if you have a bunch of events and take the union, the probability of the union is at most the sum of the different probabilities. So where have we used that? Okay, probably looks like nobody has read the book. Otherwise you would know. Anyway, I'll just tell you. So we use it at this point. So when we go from a single edge to supremum of lots of edges, single edge to supremum of tau h of 8 different edges, that's where you use the union bound. Right? So for a single edge, you get some bound of the type using shouting. For a single edge, you get that probability that that LS H minus LS prime of H where S and S prime are from a partition, where S and S prime are from one partition. Yeah, so they are choosing S and S prime are choosing uniformly from one partition. Uniformly from one partition. So the probability that this error is smaller than okay, so probability that this error is bigger than epsilon was smaller than like 2b minus epsilon square, something like that. This you will get using halving. Yeah, and you get it using this shuffling, right? So you do this shuffling here. So it's like for every index you toss a coin, toss it heads, I switch, otherwise I don't switch. Essentially, I'm averaging over m coin tosses, and that's how you get something like this here. Yeah, and then we said that okay, this is for one hypothesis. But now I want to take the union of this event over all hypotheses, over all hypotheses in H. And how many hypotheses are relevant? Only tau of 8 hypotheses are relevant. So when I take the union bound, I get the overall probability that this happens for any H in H. For any H in H. So take the union. This then becomes at most this times probability. So yeah, that's why you use union bound. So you go from a single edge to supremum overall edge. For the chance that the maximum of this thing is big. Or in other words, this is big for any edge. So that's what we did. Yeah, that's the union bound is used. Okay. Okay, so clearly you guys need to go home and study the book. Or I need to teach better. Cool. Okay, maybe we can move on now, unless there are questions. Okay, no questions. If you say ask while I'm erasing the board. Okay, so now I want to look at the second piece of this puzzle, which is that which is this growth function. Right? So what we've said so far is that if the growth function is under our control, if this is a small thing, then indeed you can learn this. Yeah, so then this class has uniform convergence, or or okay, or in other words, the variance of your losses across this class is small. So so now we really have to bound the size of this growth function. Otherwise, we have not done anything useful. So we want to say that for interesting settings, this growth function is actually a small thing. So in particular, we want to prove some level like this. Just call this Towers lemma. Yeah. Towers lemma. It says that if the visit dimension of a class is G, then the growth function is quite small. In fact, the exact statement is that this growth function looks something like summation from 0 to d m t by. And then if you do this calculation, well, this is at most E m over d times Just check. I think it should be this. No, there's not D here. What do you think? Okay, yeah. So, okay, so you can show that this is at most this. Yeah, so this, yeah, some algebraic manipulation, not very important. But yeah, so it says that if the dimension is D, then the growth function of this class in terms of M, there goes something like, this is something like M to the D. Very roughly. If you ignore the D and then E here, then it's roughly M to the D. And this is good news, right? Because if I put M to the D here, then this goes something like, D log M by square root M. And this decreases very fast. So M becomes large, this goes to 0. So it says that you can make this error as small as you like if you choose a big enough error. Okay, yeah. So this is the final piece of the puzzle, and I want to do this today. So, any questions about this? Yeah, the whole story, like why we are doing this lemma, the statement of this lemma. Maybe I'll write the course function definition again in case people have forgotten. So, tau h of M is maximum over all subsets. So we have some ground side x, right? So h is h consists of functions h from x to 0, 1. So tau h of M is the maximum over all subsets of x of size M of each C, size of each C. What is HC? HC is the restriction of H to the set C. So, write HC again. So HC here was H of C1, H of C2, H of C1. So look at the function induced on the set C, which is ordered as C1, C2. And this here is the function induced on C by H. And we want to ask how many distinct functions can be induced. So that's HC. And tau h of M is just saying that what is the maximum size of a restriction of H to C overall subset C whose size is exactly. Okay. And I'm going to do this thing now. Hopefully, you have all seen enough of this and a board. Okay, quiz question. Maybe you have a quiz in the class actually. Okay, so so let me ask a question, right? So suppose the size of C was smaller than or equal to the BC dimension of H. Okay, so let's do the other one. That's easier. So suppose this is bigger than 3 dimension of H. Then what can you say about tau h of M? Or whatever, tau h of yeah. Basically, M is bigger than this. Then what can you say about tau h of M? Okay, so what's the relationship between? Okay, so can this be 2 to the m? Or can it not be? It's an easy question. There are no tricks here. Okay, what does the dimension mean? Anyone recall? Product? Okay, you can have forwarded visual dimension also. Okay, fine. I guess I'll repeat it. So visual dimension is the size of the biggest set which is shattered by it. So visual dimension. Maximum over maximum max over t such that I'll just write it in English. Size of largest subset of X that is shattered and what does shatter mean, by the way? So when is the subset shattered by? Looks like there's something in this chart. Maybe someone has an answer. No, no answer. Okay, so what does shatter mean? Anyone remember?
If there are some points, we being able to differentiate them perfectly, classify them perfectly.
Oh yeah, sorry. I think I need to increase my volume. Can you repeat that, please?
Being able to get to a hypothesis which will classify the points perfectly.
Yeah. Hang on. I think I'm still trying a different speaker. Okay, hopefully it's close. Anyway. Yeah. So this means that there is any labeling of the subject. So H shatters. Okay, so in general, H shatters C if the size of HC is equal to the C. Okay. So yeah, let us see is finite. So finite C. If size of HC is equal to the C, that means that every possible labeling here. Remember, every label here can take 2 choices. So there are 2 to the C choices. So if every possible labeling vector here can be produced by H, then that means that H shatters that. Visual dimension is just the size of the biggest subset which is shattered. And kind of tells you how complex H is. The more complex it is, the bigger subset you will be able to shatter. So now someone should be able to answer this. So if M is bigger than visual dimension, then what is the relationship between tau H of M and 2 to the M? Now it's trivial from whatever I've said. This is less, right? Strictly less. Why strictly less? That should be easy. Okay, so I think you're lost or you haven't had breakfast and you can't speak. That was it. Okay, well, it's trivial, right? I mean, I just said that bigger dimension is the biggest subset which is scattered by H. So if M is bigger than bigger dimension, then any subset of size M is not scattered by H. Because M is the biggest thing which is scattered. So because bigger dimension is the biggest thing that is scattered, so if you go beyond it, then it is not scattered, which means that your tau H of M cannot be equal to 2 to the n. It will always be strictly less. There will be some vector here, some labeling vector which will not appear in S. So you will not have all 2 to the n vectors in S. Okay, fine. Yeah. Hopefully you understand. Yeah. Otherwise, maybe you don't. In which case, please read the book. Okay, great. So yeah, with all this set up, now we should be ready to prove this this out there. So we prove this thing. This thing is some algebraic exercise, and I will not do that. You can do it yourself or read in the book. This is algebra, which I will not write on the board. Yeah, but just remember that this is at most some m to the d. That's the thing to remember. Okay, great. So here let's prove this South lemma. Any questions about this? What statement of the lemma? What we are trying to prove? Why we are trying to prove? Okay, no questions. Okay, it may help to have a running example here, just to maybe you have to visualize. May or may not help, but let's have an example here. So let's take x to be R2 points in the plane. As we have this is some 2D plane. We have points here. And maybe your hypotheses are linear classifiers. So let's write it as here H is something like, so let's look at lines. What are lines? A line is some vector W inner product with X plus B, and if this is positive, then so indicator of this positive, or again for its sign also. So there's this for W in R2 and B. You don't get worried by notation. It's just saying that there are lines here. And let's say every or maybe half spaces. So there are half spaces here. Meaning one side is +1, is 1, the other side is 0. Okay, so the points are my x, my domain, and I'm producing labelings by drawing lines. One side 1, the other side 0. I want to find the visual dimension of this class. I'll turn out, as we see later, that visual dimension of this class is actually 3. I'm not proving this now, but prove it maybe next time. So it's will turn out to be 3. So what does this lemma tell me? That if I have some n points here, then how many different partitions can I make by drawing lines? So every partition by drawing a line corresponds to some label. According to some hypothesis here. So this tells me that number of different partitions using lines is at most what? M choose. So let's say there are n points here. Let me call it C, right? Okay. So let's say you have some subset C here. X is the whole thing. It doesn't make sense. Some subset C here, and C has size n. Then number of partitions using using lines is at most n choose 0 plus n choose 1 plus n choose 2 plus n choose 3. Yeah. So that's roughly n cube. Okay, so so that's what this lemma is telling. Just to have a picture in your head, if it helps. Okay, any questions about the lemma, how it is applied, what it tells you? Okay, no questions. Okay, so now let's try to prove this lemma. Maybe I'll erase this later. Okay, so so the idea of the lemma is to prove it using induction. So idea induction on M. Hopefully everyone has seen induction in some way or the other. By the way, anyone who has not seen induction, Vishal, have you seen induction, by the way?
Is it at some examples and then being to come up with a generalized rule, sir?
Hello? The speaker is bad. The speaker is bad. Can you say again?
Is it looking at some examples and then coming up with a generalized rule to explain the pattern? Is it induction?
Actually, your voice is very low. Maybe you can type in the chat. Oh, so it's actually at most this. It's not equal. Sorry. Yeah, sure. But no, okay. So the way you do induction is that so you so maybe I'll just write the induction framework here. So it just says that I want to prove a statement P, proposition P, for all natural numbers. I prove P of P of M. Okay, P of M is this statement that tau h of M is at most this quantity. So this is my P of M. So this is a proposition which depends on M. It takes a parameter. So there are like infinite propositions like this. I want to prove it for the infinite number of M's. Right? And I want to do what you are saying, right? I want to look at some examples and come up with this generalized rule. But how will I do that formally? I mean, mathematically, how do I look at an example and make a rule? That's not so clear. So do something very simple. You do just two things. You show that some what's called a base case is true. So basically, now some simple examples. So you show that maybe P of 0 is true. You show that P of 1 is true. Okay, so something like that. We do some simple examples. We check them by hand. Yeah, okay, maybe M is at least one. Zero doesn't make sense, right? Zero makes no sense. Okay, there's no zero. So P of 1 is true. Let's say take this one example. P of 1 is true. And then you show that P of n, I'm going to take out of m. P of m minus 1 implies P of. So you show these two things. So for m equal to 1, it's true. And if it is true for m minus 1, it is also true for m. And this is true for all m. So this is just one guy you said. So that for every m, P of m minus 1 implies P of m. And now you can imagine that for every m at least 1. For every m at least 2, I think there's no. For every m at least 2, P of m minus 1 implies P of m. And now I'm sure you can see that by combining these two, you can deduce that P of m is true for all m. So these two imply that together give you that P of m is true for all m. Okay, so why do you get this? That's not so obvious actually. Yeah, and I won't go into exactly why you get this. But intuitively, I mean, you can just think that hey, P of 1 is true. This is telling me that P of 1 implies P of 2 by putting n equal to 2 here. It's telling me that P of 1 implies P of 2, P of 2 implies P of 3, and so on. And P of 1 I have checked by hand. So by applying this, I get that hey, P of 2 must be true. Right? Then I apply P of 2 together with this and get that hey, P of 3 must be true. And so it's like a ladder. I'm climbing a ladder one rung at a time. I can reach the ladder point P of 3. I can climb the ladder one more step, and then I get P of 4. So I can just carry on this ladder building for as long as I like, and hence get a proof for everything. So I just prove these two things, and I'll be done. So yes, so this is a systematic way of doing what you said. And look at examples and build a rule. So this is yeah, some way of doing it. Okay, so hopefully you will see an example of this today. If there are questions, you can ask now. Okay, no questions. Okay, so let's do induction. First of all, let's check P of 1. So we have just one point now, right? That's what it means. So C has just one element. It's a small c. And now, well, there are two possibilities. Either, yeah, so either tau h of m is either 0. Sorry, it's either 1 or it's 2, right? It's either 1 or it's 2. Yeah, because yeah, I mean, if some happens this class, so either you can get just one label on C, or you can get both labels on C. So if you can get just one label on C, okay, then whatever you have. Actually, you don't even. Okay, sorry. Should I do it that way? Okay, so point is to think about what D is, right? So okay, so maybe yeah, okay, let me do it that way. it's equivalent, but I think that way is easier. So I do it the other way. So I don't think digital dimension D is 0, or digital dimension is at least 1. Right? One of these two cases. If digital dimension is 0, then it means that C here is not shattered by H. Because size of C is more than digital dimension. If it is not shattered, then what is tau H of 1 in this case? Who will tell me? So CH is one element, digital dimension is 0, hence C is not shattered. So what is the growth function value? Remember, growth function says that how many possible labeling vectors can I produce on C?
0, right? Sir?
I don't know how many vectors can I produce on any C of size 1. So I've taken some example C of size 1. So what can I say about the growth function value? No, not 0, right? So C can produce at least one vector always. Should be 1, right? My hypothesis class has some function, at least one function. If I apply that function on C, I will get some label. So some vector, so some labeling vector can be produced, but it cannot produce both the vectors. Right? So you have, so let's take some H in H, any H, pick anybody, and you have this vector, single length vector HC. No matter what C is. So you can produce at least one vector like this. But you cannot produce both 0 and 1. So this is maybe if it's 0, then you can produce only 0. If it's 1, then you can produce only 1. You can't produce both guys. So tau H will be exactly 1 in this case. Okay. And what is the right side? So that's RHS. And RHS here is, can choose. So M here is just 1, right? So it's 1 choose 0, and that's it, right? Go day 0. So this is also 1. So 1 choose 0, 0. Right? So they are both 1, and life is good. So 1 is at most 1. The other case is that D is at least 1. If D is at least 1, well, tau H of 1 is always at most 2, right? You know that, because it's at most 2 to the power m. 2 to the power which is 2. And what about the RHS? RHS is just 1 choose 0 plus 1 choose 1. Remember, D is at least 1. So I will get one more down here. And that is, so again, 2 is at most 2. So everything is good. And by the way, when I write this, so if M is, so when I write this notation, if I have some N choose R, then if N is less than R, then this is 0. This is 0 if N is less than R. So let's just have that convention. So you cannot choose more items from less items. Just for formality. Okay, so it's the base case P. So P of 1 is true, definitely. So So we check both cases, either D was 0 or D is at least 1. In both cases, this inequality is true. Okay, good. Any questions about this? You have found? Anything you want to repeat? Great. Okay, now let's argue the more interesting thing, which is what was called the induction step. Induction step is going from P of n minus 1 to P of n. Okay. Great. So okay, so what do we have to show? So I know that tau h of so what we know, we can assume. So we assume P of n minus 1, right? So we assume assume that tau h of n minus 1 is at most 0 b and to z. N minus 1 to z. So here we will play a small trick. So instead of proving this directly, instead of assuming this and working with this directly, we will instead work with something a bit stronger. So I will show instead that tau h of n is at most it's at most the number of subsets shattered by h. So okay, so what we show instead is that so let me write like this. For all subsets C of X, size of C equal to n. Look at all m subsets of C of X. The size of HC, which is what you care about, is at most the number of subsets of C scattered by H. So look at the subsets B of C, B scattered by H. So how many subsets like this are there? So we show claim is that the size of HC, the number of labelings you can produce on C, that knows the number of these things. And if I can prove this, I'm still done. Why? So I claim that this is at most this quantity, which I wrote earlier. Why is this the case? Why is this at most this? Yeah, anyone? This is not hard, this is trivial. Okay, it's very simple, right? So we just say that, look, default dimension is D, right? Which means that only subsets of size at most D can be shuttered by it. M choose I counts the number of subsets of size exactly I. So how many subsets can there be of size at most D? Well, these many. I just summed over every size at most D of M choose I. And so clearly this is the hypothesis. Right? So it's enough to just prove this simple thing. This implies that HC is hypothesis, and hence the growth function is also hypothesis. But this is true for every subset of size. Okay, want to repeat that? Okay. So, which part? Okay. So, first of all, why is this hypothesis? Remember, I'm counting the number of subsets of C which is shattered by it. I know that because the DC dimension of H is D, no subset of size bigger than D can be shattered by it. So I only need to care about subsets of size at most D. And let's say I don't even worry about which subset it is. I just count every subset whose size is at most D. That will definitely be an upper bound on this. And how do I do that? Well, that's what is something is telling. For every I just count how many subsets there are of size I. That's M choose I. Run I from 0 to D. And that's it.
Okay.
Okay, great. Okay, so yeah. Okay, so now let's call this thing as our P of M. So P of M is this statement. This statement here. And yeah, now forget about this expression, this KDH summation. I won't even think about it. Forget it. And let's also verify this new P of M for M equal to 1. So what is P of 1? Let's verify P of 1. So okay. Okay, so again we have some C which is singleton. Remember talking only about sets of size 1. Yeah, so once again the same argument. So so either C is shattered by H or it is not. If C is not shattered by H, then then full dimension is is exactly 0. So if C is not shattered, then this quantity is 1. Yeah, so if C is not shattered, by the way, we assume that the empty set is always shattered. So let's assume that empty set C is shattered, always shattered. It's always shattered. Yeah, so this is just something we assume for convenience. And you can think of it as saying that okay, if there are no elements, then we don't have to check anything, and therefore it is always shattered. So if C is not shattered, then this then there's only one subset here which is shattered, which is the empty set. So then RHS is 1, and then RHS is 1, and LHS is also 1 because there's only one element in H. On the other hand, if C is shattered, then RHS is 2, right? because I mean then both the empty set and C are shattered. So this is 2. And yeah, and then indeed the LHS is also 2 because I mean ST is at most 2. So yeah, this is 2, and therefore LHS is at most RHS. So once again, everything is fine. P of 1 is true. Yeah. Okay, great. Hopefully no questions. Okay, so now the thing is to prove that P of m minus 1 implies P of m. Great. So how do you do that? Okay, so the idea is to now think carefully about what kind of label vectors you can produce sets of size m, and somehow you want to relate them to label vectors on sets of size m minus 1. Okay. So here is one way to think about it, which is kind of the right way. So let me put some notation here. So let's define two sets, two sets of label vectors. Let's call them y0 and y1. So y0 is the vectors y2, y3 through ym. So that, remember, the labelings on m minus 1 things. Okay, so I'm thinking of C as C1 through Cm. Remember, I'm doing this now. Okay, so think of C as C1, C2, Cm. And now y0 here is some labeling on C2 through Cm. So here's such of m minus 1 labels such that both the extensions of this labeling to C are present in S. Okay, so labelings on m minus 1 things so that both 0, y1, y2, yn and 1, y2, y3, yn are in S. Okay. And yes, so that's y0. Actually, sorry, it's the other way around. Here it's on. Okay. This is on. Let's try one. This is on. One of these is in SC, and by1 is the other. By1 is when they're both in SC. This thing. Okay, so this is not both, but at least one of. So if at least one of these things is in SC, then we say that this vector on n minus 1 things is in y0. And if both of this thing and the other extension are in SC, then we say that this vector on n minus 1 thing is in y0. Okay. So we have classified the label vectors on n minus 1 into two categories. So okay, I mean not much about every label vector, but there's some interesting label vectors. Okay. So okay, so let me ask a question. So again, let's look at these lines. So let's say I have so yeah, we're going to draw a nice image. Suppose this is my C. Okay. C1, C2, C3, C4. Okay. C is this side. And let's say that Y2 to this label vector here is so Y2 through Yn, so MS4. And let's say my label vector was 1, 1, 0. Okay. So label 1, label 1, label 0. So can someone tell me? Okay, so is this label vector in Y0, Y1, or none of them? Remember, I'm talking about my hypothesis class here is the set of half spaces. Okay. So is this label vector 1, 1, 0 in Y1, Y0, Y1, or none of them? Okay, how will you check that? Let's try the labeling. Okay, there is no Y1 here. So let's try the labeling where Y1 is 0. So if this is labeled 0, okay, so is this an XC or not? Labeling of this is 0, this 1, this 1, this 0. Is this an XC or is it not an XC? Is there a line which puts these two on one side and these two on the other side?
No.
No, right? There's no line like that. So, yeah, so indeed, 0, 1, 1, 0. So if I put a 0 here, then this would not be an XC. The other thing will then automatically be an XC because I mean, because yeah, I mean, I hope you see why. But yeah, the other thing will be an XC. And this is not always the case, but in this case, the digital dimension is 3. This will be the case.
1001 will not be.
No, 1, 1, 1, 0. So this is 1, then it is in this.
This will be.
Right? I mean, you can just draw this line. So a partition like this. So that's the next thing. So yeah, so this particular labeling. So what it tells me is that 1, 1, 0 is actually in Y0. Yeah, so that's what it's telling me. On the other hand, if this point was at a different place, maybe this point was here. So again, let's look at 1, 1, 0. Maybe my C1 was actually here. Now, okay, maybe it's different. So suppose C1 was here. Now I can produce both labelings. So, for example, the labeling is there right now produces 0, 1, 1, 0. And if I draw a line like this, then it produces 1, 1, 1, 0. So yeah, so then yeah, so C1 was here. I can produce both labelings. I can produce both this guy and this guy. So with this configuration, yeah, so if I see how to do with this, then 1, 1, 0 would have been in 5. Yeah. So whether a labeling is in y0 or y1 depends on what C is, how C looks like. Yeah, that's why everything is defined for one C. So you just check if I can extend this labeling on C2 through Cn to both labelings on C1 through Cn or not. Okay. Good. So yeah, so that's y0 and y1. Now, why are we defining these things? What's the point? The point is that I claim that HC is exactly y0 plus 1. Remember, I want to count the number of hypotheses. Here, the number of vectors, number of label vectors in HC. In that number of label vectors is exactly y0 plus y. Can someone see why? Kind of trivial, falls from here, but can someone tell me why? The point is simple, right? Any vector, any label vector in HC has to be of two types. Right? So let's pick a label vector y1, y2 to yn. Okay. In HC. So let's ask if the corresponding vector 1 minus y1, y2 through yn, which is the other vector. So I've flipped the label of the first point. Is this an HC or not? The first guy is an HC, and I ask if the second guy is an HC or not. So that's essentially what's going on here. So okay, so what's happening is that y0 is counting 1 for every label vector for which yeah, only this guy appears, but this guy doesn't appear. And this is accounting for label vectors where both appear. Does that make sense? So okay, let me write it like this. So let me write it for formally. So I claim that erase this now. So y0 is exactly the number of number of y2 to yn. No, okay, sorry. Oh, sorry. This is a bit confusing, but to say it. Okay, let me put it like this. So y0 is just the number of y2 through yn, such that y2 through yn appears. Yes. Yeah, I think maybe I'm going too fast. Well, let's just do it next time. I think let me not rush. It's no point. So, I would suggest you look at this proof in the book. Maybe that will help. And next time we can do it, in full detail. I think I maybe rush it. That's why people are getting. Okay, so we start from here next time. This definition. So I will not repeat the definitions again. Hopefully, you will all remember them. I will write this statement, and I will try to prove this. And I start with these definitions of y0, y1. And I'll start from this point. Okay. Thanks. Yeah, but please read the book. Otherwise, you will be lost in class. Yeah, at least please refresh whatever we have seen so far.
Yes.
Okay, good.